All right, so last time we talked about we introduced the mixture theory and talked about the um, momentum balance for the solid, basically, the momentum balance for the solid fluid system. And in the end, we didn't get anything that looked that much different than the regular momentum balance. It's just with the understanding that the stress is now this effective stress. So we introduced this concept of effective stress and derive the BO coefficient, all that stuff. So today, let's talk about the mass balance of the fluid. And if you remember, we wrote everything, or I said last time that we're going to write everything on sort of on the back of the solid skeleton. So what we're really talking about here is the mass balance of the fluid in the solid skeleton and any fluid entering or exiting the solid skeleton as it deforms. Okay. And so let's just write down the mass balance as we derived it before. I'm going to, on the divergence operator, I'm going to write a little x there. It's sort of always implied or implicit because when we derive all the equations, everything's in terms of the current coordinates. But now we're starting to take everything back to the reference coordinates of the Lagrangian frame, right? And that's what we did last time, and that's why we used the Piolo-Kirchhoff stress instead of the Cauchy stress. So, but this is the mass balance equation as we derived it in the current frame, okay? And here we're talking about the fluid, right? So let's just put some superscripts. We're talking about the mass balance of the fluid. And according to our definition, remember last time we introduced that if I have the superscript, this is the intrinsic density. So this is the density of the fluid, or I'm sorry, the mass of the fluid divided by the volume of the fluid, right? But we also introduced the concept of volume fraction, right? And so we said that we can write the intrinsic density as the volume fraction of the fluid times the fluid density. And then now this time, this is the fluid densities. This is, you know, the regular fluid density that you would measure. Right? I'm sorry, I misspoke. Let me just rewrite over here. So the intrinsic, this is the mass of the fluid over the total volume. Right? This is the normal density you'd measure. So this is the mass of the fluid over the volume of the fluid. Okay? And so then they're related through the volume fraction. Okay, and what's another word for the volume fraction of the fluid in our system of because you know I introduced this as a generalized sort of mixture theory way that so you could include multiple species, right? But in our case, where we just have two species, a solid and a fluid, okay, then what would be another word for the volume fraction of the fluid? It's the porosity, right? It's the volume of the fluid in the pores, right? If it's not the volume of the solid, then it's the volume of the fluid in the pores of the solid, right? So in this case, this definition, it's, you know, I can also say porosity, and you may hear me say porosity going forward. So anyway, going back to our mass balance equation and just plugging in that relationship. What? The superscripted density, right? All right. So now over here, I want to write down, I'm going to define a new vector. Let me just write down what it is. I'm going to call it W. So what W is it's the relative mass flux. The relative mass flux in or out of the solid skeleton. All right. So if I solve this equation for VF, then I have 1 over this guy. And so now I'll just plug that in to our mass balance equation. So then I'm going to get this, okay? Now, does this look like anything to you? Kind of. I mean, don't you remember when we defined our material time derivative operation? It was something like this. Something like that, right? So this thing right here sort of looks like the material time derivative of this quantity under the motion of the solid skeleton, right? So if you'll allow me to do this, I'm just going to say ds, okay, df rho f dt plus this equals to 0. And in fact, going forward, I'm even going to drop the little superscripted s on the time derivative. All right. So from here forward, I just want to make the point that the material time derivative is defined on the back of the solid skeleton. Okay. So the convective term has the velocity of the solid in it. Okay. When we're talking about the material time derivative for the rest of what we're going to do here. Okay. So also remember, this is the pointwise conservation of mass that is equivalent to saying this, right? And in fact, when we first derived it, this is how we derived it. It's the density in V plus any mass flux in or out of V. Well, V where S is the surface of V, right? Okay. And so then if you remember also, we had this thing called Nansen's relation. We used it when we then derived the Piola transformation. And this is how we take tensor and vector quantities from the deformed to the reference configuration. And Nansen's relation specifically deals with unit vectors. So unit vectors in the current or deformed configuration and how they transform into unit vectors in the reference configuration, okay? So via Nansen's relation, we can define a new vector W that's in the reference configuration, right? And it's going to be JF inverse W, little w, okay? And then we're also going to introduce something called the Lagrangian porosity. So this porosity that we've been using, is the current fluid volume over the current total volume. And the Lagrangian porosity, or volume fraction of the fluid, however you want to say it, is the current fluid volume over the reference total volume. And how do you think they're related? Yeah, through the Jacobian determinant, right? Anytime you just have a transformation of a scalar field of coordinate through a coordinate frame from the reference to the deformed, it's just through the Jacobian determinant. So this is the Lagrangian porosity. Okay? And so with these two things, Nansen's relation and this pullback operation of the Lagrangian porosity, we can write sort of Lagrangian form of the mass conservation on the back of the solid skeleton. So now this divergence operation is with respect to big X, the reference. Right. I'm going to call this equation star. So we're going to first look at the left-hand side of star. So the left-hand side of star, if we use the chain rule, this I'm going to use this superscripted dot notation and the material time derivative interchangeably. So that's just material time derivative. Again, on the back of the solid skeleton. Okay, so that's the left-hand side of star after we use the chain rule. And the first thing we're going to do, let's look at the material time derivative of the density. Okay. So we're going to assume, or we're going to make the barotropic assumption. So this assumption is that the density is only a function of what? Pressure. Okay. So then if we want to take the time derivative of this guy, using the chain rule, we'd get partial rho partial p dp dt. Okay. So you might recall, does this thing look familiar to anyone? Who's had petrophysics? So you probably remember from petrophysics a relationship between the compressibility is 1 over rho f dp, right? So that's the compressibility of the fluid. Of course, we don't really use compressibility. We use bulk modulus, and 1 over the compressibility is the bulk modulus, right? So with that, we can get that partial rho f partial p f is equal to this guy, right? So that'll allow us, we can just go ahead and we'll plug that in for this term right here, pf over kf. Right. But we can do something else with this guy, right? We can integrate both sides, right? So if we just rearrange it and integrate from, say, some reference fluid density to the current fluid density, kf over rho f d rho f, and then integrate from some reference fluid pressure to the current fluid pressure, well, if you work that out, you get this guy. What is this equal? The current density over the reference density? Remember from the Lagrangian form of conservation of mass? Remember there was 2 conservation of masses? One was completely in Eulerian, one of them was in Lagrangian. If you go back in your notes, that was a recorded lecture that day I was out. But if you go back in your notes, you'll see that that's equal to the determinant of f, right? Which is equal to, we call J, right? Okay. So now if we take the natural log of both sides of this equation, we get the log of J is equal to Pf minus Po, right? And I'm going to go ahead and multiply through by Kf so that it shows up over here. Okay? Now, let's take the time derivative of the material time derivative of both sides of the equation. So we get d dt Pf, that's a P. I'm trying to make my rho's and p's distinct here. So that's d dt pf is equal to d dt or kf d dt log j. All right? And that's because on the right side you have d dt pf, and then distribute, you have d dt pf0. Well, there's no time dependence on the reference pressure, right? So it's 0. All right. So now we have this guy. Now we have that right here. So we'll plug it in. Kf d dt log j. And the kf's cancel, so that ultimately we have pf d dt log j. All right, so that takes care of this term. Now this guy, we're going to use a constitutive model, okay? So that for the time rate of change, or the material time derivative of the change in porosity, I'm just going to write it down. So d dt what? Oh, gosh, why didn't you guys tell me? Should have told me by now. Sorry about that. So this is Athy's pressure porosity relation. Assuming a small change in porosity over infinitesimal time. So if you remember, if you took like undergraduate reservoir geomechanics, you remember there was some relationship between porosity as some function of the reference porosity, e to some parameter, so some function like that. Well, essentially this is the same thing for finite deformations, right? And then it actually comes out a little simpler when you write it in terms of the time derivative. Okay, so this is just a constitutive law, okay, for the porosity. And so if we distribute the material time derivative and do some algebra, then assume the case when the pore pressure is much, much less than the bulk modulus of the solid. That allows us to simplify this sum. All right, and so that's just, this. So that's just this d porosity dt term. But if we put everything back on the left-hand side back together, then ultimately star becomes where m is BO's modulus. So then we're going to use Darcy's law. So Darcy's law is a constitutive relationship for the relative flux, right? So the difference in the fluid velocity and the solid velocity, which, remember, we had defined W. So that's going to be equal to kappa, and that's a tensor, over mu minus, and this is the gradient with a little x, the fluid pressure, where g is the acceleration due to gravity. So this is in Eulerian form, right? But if we do a pullback operation into the reference configuration, because everything appears in the reference configuration, and we get K. So this is the Lagrangian. And this K represents the full pullback to the reference frame of that little k tensor. Where kappa is a permeability tensor. So this guy, that's, and then you put this on the right-hand side, that will give you your full conservation of mass equation in terms of everything in the reference coordinates. Kind of ugly. So I got done a little early today. I thought that would take longer to get through. But so next time we'll talk about the linearization. When we go to solve this, so after Friday and the test, we're going to start kind of switch over and start talking about computational setting. And we won't actually solve all this finite deformation stuff. It's going to be difficult enough to do it because there's going to be a lot. I mean, I don't know how good a programmer everyone is, and so there's going to be a lot of code to write, and just there's enough difficulty in the small strain formulation. I wanted to give you the full finite deformation theory so that if you need it, you can come back to it. By the way, most of what I did today follows a recent paper. When I post the notes, I'll post that paper, or maybe I should not post the paper, but a link to it if you're interested in seeing, all the details. There may be actually a few details in my notes that aren't in the paper, but nevertheless, I'll post that. So anyway, I wanted you to see the full finite deformation theory in case you find yourself in a scenario where you need it, a problem that has large rotations or large deformations leading to material failure and other things like that, okay? But now when we start doing the computations, we'll just use the small strain theory. And so we need to linearize these equations, right, so that we can get to small strain. So remember, in small strain or linearized theory, we make no difference between the reference and the deformed configurations. They're one and